for having me here. Even though I'm sort of an outsider to this community, but hopefully I'll tell you about some of our recent results, which some of you might find interesting, particularly with respect to the kind of things that we heard in the morning in Valentin's talk about dimers in Rydberg atom arrays. Okay, so what whatever I'll tell you is summarized in this recent preprint, which was in collaboration with Sergei Moroz at Karlstad University and Ankush Chobe, who was a PhD student in our group and just left for his postdoc at Karlstad. I'll tell you about how to realize spin liquids in a square lattice starting with dimers. And this problem turns out to have a rather old and rich history with lots of barriers on the way. And I'll try to tell you about some of the interesting progresses that we think we have made recently. Okay, so just to set the tone, trying to understand various phases of quantum matter, we now realize that there are these 4 big chunks. The most familiar ones are the symmetry broken phases like ferromagnets and superfluids. But as we go along, there are the more and more quantum phases in the sense that entanglement becomes important, and we get symmetry protected topological phases like the topological insulators or integer quantum Hall, or more long-range entangled phases like fractional quantum Hall states and spin liquids. And the things that we understand least about are these strongly correlated metals and stuff like that, where basically gapless phases of fermions at finite densities. Okay, so apart from this symmetry broken phases, essentially all the things that we learn in master's courses needs to be revisited, and this is because of the following reason that in particular when we start from some high energy descriptions of ions and electrons and try to go to a low energy description, which often is what experiments probe, the symmetry broken states and the framework mostly due to Landau and others, work because the resultant states that we get at low energies are almost product states. This is why even though we start from a very quantum system, we sort of get a renormalized classical picture, and this is why the mean field theories work, the Landau-Ginzburg theories work, the Gross-Pitaevsky type of description that we heard in the last talk work, because we have this sort of semi-classical picture. But this, of course, doesn't work for the 3 other quarters. And what happens is that when we go from high energy, typically when we cool the system, the thermal entropy is gotten rid of by superposing and leading to many-body entangled states. And these do not have any quantum classical descriptions. And the way that it appears in the when we try to describe these systems at low energies is that the high energy Hilbert space, which has a tensor product structure, often does not survive at low energies or IR. The symmetries which were rather the symmetries which were present in the microscopic degrees of freedom often become sort of non-uniquely implemented, and their representations become more mathematically complicated. They become projective and things like that. And because of the entanglement, we generically get to a long-range interacting theory, which is given in terms of naturally given in terms of a gauge theory or generalized electromagnetism. So these are the reasons why we need to understand and revisit many of the things that we know so well for symmetry broken states. And one of the places that has, over the last 30 or 40 years or maybe more, has served a lot of information are these dimer models, originally thought in context of frustrated antiferromagnets, in the sense that when we take two spin halves interacting antiferromagnetically, they lead to the ground state is a dimer or a singlet, and when we take many such spins in an unfrustrated situation like a square lattice, nearest neighbor Heisenberg magnet, these dimers don't survive in as low energy degrees of freedom, and we get magnetic order. But when we have frustrated interactions, the dimers and the spin full excitations, the spin gap may survive, and the dimers remain good low energy degrees of freedom. Now, the problem with dimers is that if I think about, say, a square lattice and count the number of dimers, there is one dimer per every bond. So if I think about a dimer number, which can be 0 or 1 in absence or presence of a dimer, then the dimer number faces a constraint that at the spin half at one side can be a part of only one dimer. So if I go count the number of dimers starting with one side, that is constrained. So this is basically this Hilbert space, tensor product Hilbert space structure breaking down. And in other words, the dimer Hilbert space does not have a tensor product structure. And so that so the counting goes, the counting of dimer number, the dimer covering goes in this way, whereas the spin Hilbert space has a tensor product structure. It's just 2 to the power n. So while I mentioned this in context of spin halves, these can be realized in various kinds of other situations, as we heard in the talk just before coffee in the morning. So once we have these degrees of freedom, say the dimers, and because the Hilbert space is not tensor product, the symmetries may not act in the usual way, and the interactions now lead to rearrangement of dimers without breaking them apart at low energies, and has this constraint. So typically, if one tries to write down Hamiltonians for these dimers, they have a potential energy which basically counts the number of dimers in each plaquette, and the kinetic energy which rearranges dimers locally. So these kind of, the Hamiltonians were written quite early in late 80s in context of high TC cuprate superconductivity by Roxer and Kivelson and various other people. And so again, just to point out, the potential energy term basically counts the number of dimers in a plaquette. If this number is negative, it favors having the 2 dimers in a plaquette, and it penalizes 2 dimers if this number is positive. On the other hand, the kinetic energy basically leads to this kind of flippings back and forth for these dimers, and that's essentially the dimer dynamics. Okay, so these Hamiltonians were beaten to death. These go under the name of Roxer-Kivelson Hamiltonians, and on a square lattice, what was found after 30 years of intense numerical and field theoretic understanding, that they give rise to a dimer, mostly dimer crystal phases, otherwise known as valence bond solids, as we heard in the morning briefly. So when omega, this potential term is positive, we get a staggered phase where each plaquette contains 1 dimer. Whereas if the potential term is negative, then we get every plaquette contains 2 dimers, and these are various kinds of crystalline phases of dimers. Except for this fine-tuned point where these 2 coupling constants, the kinetic energy and potential energy, are exactly same, when we get what is called a Roxer-Kivelson point, and at that point, one can exactly solve this Hamiltonian, and the ground state is basically an equal superposition of all dimer configurations. And that's a very interesting state because it has long-range entanglement, and which is realized only as a critical point between these 2 solid phases. And this particular wave function belongs to what is called a resonating valence bond liquid, more precisely a yuan resonating valence bond liquid. In this class of bipartite lattices, this only occurs as a critical point, and so it's basically the same thing here. We have the staggered phase and the columnar phase and the Roxer-Kivelson point, where the ground state is equal superposition of all dimers. So it does not have any particular order, but finite many-body entanglement. So this was again investigated, extended in various directions, and what people found is that generically the kinds of valence bond solid ordered phases, the solid phases change from the staggered or the columnar that I just mentioned to various other kinds of solid phases, but the resonating valence bond liquid phase, the resonating valence bond that is realized at the Roxer-Kivelson point never becomes a phase. Okay, and just as an historic anecdote, this basically played an important role in sort of collapsing the program that was started by Phil Anderson, etc., to try and understand the high-TC cuprate superconductors as doped RVB, because the RVB could never be realized as a phase in this class of models. Okay, so what I'll try to tell you is that a particular qubit regularization of this dimer model can actually lead to a generic phase diagram which contains Z2 topological liquid in the same spirit as a short-range resonating valence bond solid, resonating valence bond liquid, and the entire phase diagram, a part of which I showed you in the previous. So this actually generalizes to something this, which is what we reported. Okay, so with that, let me start with the details of our constructions. So what I'll tell you in the next 20 minutes or so is a particular qubit regularization of the dimer Hilbert space, and this contains two important steps which I'll go through and then walk you through the field theory and the phase diagram. So the first step is mapping of the dimers to dual bond Ising spins, and then implementing the dimer constraints by a particular kind of energetic penalty instead of the projection that of removing all the spinful excitations. So let's just remind ourselves that the dimer number is given on every bond of the square lattice by this number 0 or 1, and at every site there is a dimer constraint that there is only one dimer per attached to every site. Okay, so let's go through these two things in steps. So let's these red wiggly bonds are the position of the dimers, and so I have some dimer state, and if you see that every site is connected to one dimer, and this is a fairly random. So let's think about this black lattice and define Ising spins Zij to be plus or minus 1, and every time this I and J bond crosses the dimer on this red lattice, I define an Ising spin on the dual lattice via this relation, so that whenever I have a dimer, this Zij is minus 1, and whenever there is no dimer, the Zij is plus 1 on the dual black lattice. Okay, so this is the mapping, and then the one dimer per site, which is this configuration, in terms of this dualizing spins, becomes this constraint. Okay, so this is just a rewriting of the degrees of freedom. Okay, yeah. No. So the dual spins live on the bonds of the black lattice. Okay, or the dual lattice. Okay. So if I do this, this is just rewriting of things. So the dimer kinetic energy term becomes so these are the two dimers, and they flip to become horizontal dimers. And in terms of since the Z variables count the number of dimers, the X, which is conjugate to Z, or the X Pauli matrix, basically flip the dimers. So this kinetic term becomes a product of 4x on the dual lattice. Okay. Similarly, the potential energy term turns out to be some Ising interaction, next nearest neighbor Ising interaction term, the details of which is not important, but essentially this is rewriting of the dimer model. So that covers the first the step of the mapping. The next step is to implement this single dimer constraint via energetic penalty. So remember this, the dimer constraint was one dimer per site, and which in terms of these Ising variables is the sum of Z over a placate is equal to 2, which is essentially using the mapping just, okay. So let me try to point out that there is a energetic penalty that can be implemented by this Hamiltonian called H constraint, which has two terms. So the first term is basically take a placate of the dual lattice, which is this black lattice, and take the product of all the Z sitting on the bonds, and weigh it with a positive amplitude. Okay, so that's kappa. So what this term wants to do is, when kappa is positive and very large, it wants this number to be this product of 4 Z's to be -1, and that basically means that either 3 Z's on a placate are negative, or 1 Z on a placate is negative, and this is 1 Z on a placate is negative, which has one dimer, but it also contains the 3 dimer, where 3 Z's are negative on this placate, which corresponds to an unphysical 3 dimer configuration, which the first term is blind to. The second term actually lifts this degeneracy for J greater than 0. So it wants to minimize the number of Z spins which are down, and that basically leads to splits this 1 dimer and 3 dimer degeneracy. And once we have this, energetic potential term added to the dimer model, it essentially is a faithful representation in the kappa and J going to infinity of the dimer model. But the advantage of this is that now that I have implemented the constraint via energetics, my Hilbert space has a tensor product structure, and this is one where one can do lots of numerical calculations more carefully and analytically track down various things. Okay. So once I write down everything together, this is the Hamiltonian where these spins now sit on the bonds of the dual lattice. And what I'll try to tell you is the phase diagram of this model in this kappa going to infinity limit at finite J as a function of the kinetic term and the potential term of the dimer, and finite J would allow this mixing of the 1 and 3 dimer configurations, which would open up the Z2 spin liquid, as I'll tell you. Okay, so let's go ahead and try to do this. So the first thing that one wants that would be very useful is to think about putting omega equal to 0, so no potential term, and taking gamma to be large, which is larger than J, which is much away from the dimer limit, and start from there. So once I do that, I put the omega to be 0, and think about this kinetic term becoming very large. The Hamiltonian essentially reduces to this, which is again another well-known exactly solvable model from the works of Kitaev in late 90s or mid 90s. This goes under the name of toric code. Okay. So what happens is that in this limit, the Hamiltonian contains two terms. You take the placate and you take the product of the four the z components of this spin half, and that's the first term. And then the next term is basically you take a site and you take the x components of the four spins connected to that site, and this is the effective Hamiltonian in this large gamma omega equal to 0 limit. And this is exactly solvable, as many of you know, because these two terms in the Hamiltonian commute with each other, and the ground state is obtained by having the product of the z's at every placate to be -1 because kappa is greater than 0, and the product of x at every site to be +1, and this goes under the name of pi flux toric code. Okay, so this is a Z2 spin liquid because so this is a Z2 spin liquid because the ground state is actually given by a superposition of closed loops where every placate has the Z equal to -1. And you think about one way to construct the ground state is to think about a reference configuration where every placate has Z equal to -1. Say every alternate rows have Z equal to -1, and then you act a projector like this, which generates loops of flip spins on top of this background. So the ground state is a immense superposition of these closed loops, and because we have these closed loops, if we try to calculate bipartition entanglement entropy, these closed loops either don't cross the partition or cross the partition twice, and that leads to this. So basically, there is one qubit of information non-locally stored in this wave function, which is the parity of crossing of any bipartition, and that's the origin of this -log2 topological entanglement entropy. So the point is that once you have this Z2 liquid, you cannot, because of this -log2, you cannot smoothly deform this wave function to a product wave function, and this represents a Z2 topological order. Okay, so that's the fate of this Hamiltonian in the large gamma omega equal to 0 limit. Now let's take keep omega equal to 0, but reduce gamma so that I have this Hamiltonian, and I am increasing J so that I'm going towards the small gamma limit of this Hamiltonian, still the potential term to be 0. So of course, this Hamiltonian no longer remains exactly solvable. You can put it on a computer. In particular, we did DMRG on cylinders which are infinite in one direction, but perimeter of 4 in the transverse direction. And once you try to understand the numerical data, what I'm showing here is the bipartite entanglement and entropy. So you see that at large gamma, this has an entanglement entropy which saturates in the to this value, which is what is predicted from the exactly solvable model of toric code. But as you reduce gamma, it undergoes a transition to a low entangled state, and in fact this transition is better characterized by the correlation length, the largest correlation length of the system that you can track, and so it shows that there is a phase transition as you go from large gamma to a small gamma, and the large gamma phase is nothing but the Z2 liquid that I just discussed. Okay, so in fact, you can do this over the entire phase diagram, and this is where I'm showing numerical data of these data points are for the largest correlation length, and you would see that there are two lines of phase transitions as signaled by the correlation length data, and this is one set of lines, and this is the other set of lines. and this is the large gamma phase, and this is what the spin liquid is. So let me try to tell you what these other phases are and the resultant phase transitions and how to describe them. Okay, so to characterize the large, to characterize this small gamma phases or the large omega phases, what you can do is you can try to calculate since these are low entangled phases, you can try to ask various kinds of dimer order parameters, and these are nothing but the columnar and the staggered dimer crystals that I briefly alluded to in the beginning of the talk while discussing the Roxer-Wilson model. So what happens is that if you try to plot the order parameter for the staggered arrangement of the dimers or the columnar arrangement of the dimers, they become non-zero in the respective regions, and this is exactly what you would expect from the analysis of dimer models. And in fact, in the large J limit, as we discussed, the large J and large kappa limit, the Hamiltonian indeed reduces to dimer model. Okay, so given these phases, and particularly the fact that you have a entangled phase up here, and you are undergoing transitions from a Z2 liquid phase to a dimer solid, we need to ask what are the phase transitions and how should one think about these transitions. And since the Z2 liquid is long range entangled, so the the usual Landau theories based on order parameters do not work, because the Z2 liquid, as I'll show you, have anionic excitations, and any Landau theory based on only order parameters completely misses the Z2 liquid. Okay, so let's try to do that. So going back to the Z2 liquid in this large gamma, the ground state, of course, has obeys this. But if one wants to create excitations, one basically flips this product of Z's around the plaquette from -1 to +1, and product of X's around the site from +1 to -1, and these are the basic excitations. Now, the point is that these basic excitations behave not like Goldstone modes or the low energy excitations of a product state, but rather the charges of electromagnetic theory. In particular, they behave like this product of these Z excitations behave like magnetic charge, and the X excitations behave as an electric charge, which is fairly easy to see by taking a Z excitation around an X excitation, and you would see that they see each other as source of pi flux, just like as you would expect from an Aharonov-Bohm effect. So there are these two excitations, which are these mutual semionic, mutual semions, in the sense that they see each other as source of pi flux, and they are the fractionalized excitations of the Z2 liquid, which forms the right degree of freedom to write down the low energy field theory. So both these excitations are bosonic, but they have this mutual statistics, which is why the Landau theory misses it. Okay, so one can think about what happens when one starts with these Z2 liquid and considers the effect of this Zeeman term, which is this J term. And what this J term does is to create electric charges, creates and moves electric charges. And so what one needs to understand is what is the effect of this motion of these electric charges in the background of this Z2 liquid. Okay? So what happens is that because of this J term, the electric modes, the electric charges gains dispersion, and since the background flux is because the product of Z is -1, they see a background pi flux, and the charges moving in background pi flux generate soft modes, in particular 2 soft modes which are related to projective implementation of translation symmetry. And essentially what happens is that these 2 soft modes serve as the long wavelength low energy fields that describes the transition. So as one increases the J, the gap from the soft modes becomes lower and lower, and they collapse when gamma is of the order of J. And when these, since these are bosons, they condense, they give rise to these kind of crystalline order. Okay, so the point is that to understand this transition, one must track the effect of these the dispersion of the soft modes and their interactions to write down the appropriate field theory, which is not in terms of the order parameter, but so to say, in terms of these fractionalized excitations of the liquid. Okay, so one basically does the things similar to the Landau-Ginzburg theory, but for these fractionalized fields, and finds out how they transform under various symmetries of the lattice, and tries to write down a low energy field theory in terms of them. So note that the low energy field theories are in terms of these E and M charges, which are not order parameters, and they follow various kinds of various non-trivial implementations of symmetries, and they give rise to the semionic statistics generally gives rise to Chern-Simons field theories, which is what the low energy field theory boils down to. Okay, so one can follow this line of ideas and write down the quantum field theory allowed by symmetry and things like that. So it has various kinds of terms, which the topological nature of the Z2 liquid is embedded in the analysis of this term, which I won't go into, but let me point out that there are 2 parameters in this field theory which can be tracked back to the 2 parameters of the microscopic model. One is the mass of the electric charge, and the other is the kinetic the kinetic energy of the electric charges. And these are the 2 parameters that you can effectively tune in your field theory. And once you try to understand this field theory in terms of these 2 parameters, this is the phase diagram that you get using within one loop renormalization group calculation. Let me just quickly walk you through. So when the electric charges are gapped, this is the R is the mass of the electric charges. So that's this top part, the top half of the phase diagram. So the electric charges are gapped, and then this term is generically irrelevant. This is a high gradient term, and you get a Z2 liquid. So all these complicated things can be set to 0 because these phi fields are the soft modes are gapped, and the Chern-Simons theory basically recovers the right topological data for the Z2 liquid. Whereas once you condense the bosons, depending upon whether the high gradient term is positive or negative, the gradient term is positive or negative, you recover the various kinds of the crystal phases, the staggered phase, the columnar phase, and the Roxer-Wilson point buried somewhere here. So this is essentially the entire phase diagram, and that you can get once you allow these 1-dimer, 2 to 3-dimer fluctuations. And you can sort of find the numerical justification for these the one loop RG phase diagram, and one can make various things quite concrete even within these DMRG calculations on a cylinder. So let me just end by pointing out that the very interesting thing from the field theory point of view is this multi-critical point where you need to tune two parameters to reach a multi-critical point, which is a multi-critical Yuan liquid, which is generically unstable, different from the Roxer-Kivelson Yuan liquid. And once the multi-critical Yuan liquid actually gives a natural way of understanding the phase diagram. So starting with this Yuan liquid, you condense the charge to Higgs scalar, which is basically the microscopics is controlled by the mixing of the one dimer and the three dimer configurations, and that gives you the Z2 liquid. And this essentially was absent in all the older dimer model calculations. But you can also undergo monopole confinement because it's a compact Yuan theory and describe all these various kinds of dimer crystals. So that's essentially what I'll end up with. I've told you about a particular qubit regularization of the dimer model, interpolating it with the Tori code, and this overcomes the usual Yuan confinement that people have been facing in order to stabilize short-range RVB. There are various ways of understanding this phases, starting with the multi-critical Yuan liquid, which is different from the Roxer-Kivelson model. Okay. Thank you.
Thank you, Subhro, for this very interesting talk. I'm sure there are questions.
Thank you for the very nice talk. So I wanted to go back to the original model. So in these timer models, the Hamiltonian that described them is a Heisenberg model. I just wanted to see, because it seems Heisenberg models are easier to implement experimentally. So do you know what I need to do to my Heisenberg model in order to get?
You mean the Heisenberg spin model?
Yes. So you will started to write the Heisenberg model at the beginning as the source.
Okay. So let me go.
Yes,
yeah.
Exactly. So you were saying that starting from this S.S model, you got the timer.
Yeah, so one can try to do that, but you have to, so the underlying lattice, etc., needs to be chosen so that you have a frustrated interactions, so that the spin gap does not collapse.
So exactly. Okay? So if I have an S.S model in a Kagome lattice or something.
Yeah, so the Kagome lattice turns out to be particularly bad because the spin gap collapses and the particular liquid that you realize is not this one.
Okay, so what lattice should I get? Is it clear?
Yeah, so I think that the right lattice is, again, square lattice, but starting with J1, J3 interactions.
Okay.
Okay, so J1, J3 interactions, and maybe we should discuss that, seems to be the right lattice, seems to be the right spin Hamiltonian to start from, which realizes this physics.
I see.
Okay.
Okay. Thank you.
Note that this is not J1, J2.
Yes,
that yeah.
The answer.
Okay, yeah.
But another question that I had is, what is your order parameter for those phase diagrams?
Okay, so the order parameter is basically some correlation function in the language that I described is a correlation function of these Zij on one bond and Zij on another bond. Okay, so from those basic correlation functions, you can construct various kinds of dimer order parameters. So the Fourier transform of them peaking at different momentum values signify different kinds of dimer crystals.
Can you go back to that action that you showed towards the end of your talk?
Yeah.
Yeah. So it seems that the cos 4 theta term is missing, and that's
because
of some symmetry.
Yeah. So the cos 4 theta term is missing because doubled monopoles, doubled instantons are disallowed. Only quadrupled instantons are allowed.
And this term W is dangerously irrelevant.
This term is dangerously irrelevant at the critical point. This is actually, I mean, this is actually the same term that I think you and Subir and found, but coming from a completely different calculation in terms of the electric soft modes.
Are there any other questions? If not, then let us thank all the speakers of the session.